Hey, how's it going? Going to explain the translatable patterns that come from this clever sequence of digits. To do so, let's begin with every single number that's involved in this pattern is based on the properties of the number 9. Every number that you're currently observing is a multiple of 9. The numbers 108 and 72 are key numbers in this version. There are multiple versions that you can observe. They will all lead you to the exact same place. More on that in another video. For now, we're focusing on this version. I'm going to explain how to add and subtract with these numbers to find the patterns that are relevant, which are translatable to show us two-dimensional and three-dimensional and beyond. We'll start with the 108 and the 72, since those are key numbers. 108 plus 72 equals 180. I think that's pretty obvious because we're looking at the internal angle and the external angle of a pentagon. Every angle, internal and external, added together will always equal 180. And the number 90 will always sit exactly in the center of them. To carry on, 108 minus 72 gives us 36. We're going to play the same game with our new results, 180 and 36. 36 plus 180 equals 216. 180 minus 36 equals 144. Conveniently, 108 doubled is 216. 72 doubled is 144. In reality, what we're looking at is a doubling sequence, or you could say it's a halving sequence. To be more precise, though, you can see 6 columns here at this moment in time. You can expand it any way, as far as you want, to the left and to the right. You don't need to. What you need is this column, and this column. You only need 3 columns. But what you also need is 13 rows. More on that later. For now, since we're aware that there's definitely something happening with these numbers, they all work together, we're going to have a quick look at what these patterns translate to. So I'm going to zoom out now, make it a little bit easier for you to see this right here. Zoom out all the way. As you can see, the formula itself, it is actually complete, because like I said, you don't have to carry on with this information. You notice the number 360 and the number 432 there, and we've got the 360 and the 432 there. So it's literally, they repeat, but they just shift down by 1 point. So these 2 columns here, both together, move over. Whereas on this side, we have, well, 36 is half of 72. So the 36 that existed here, we don't need to worry about that. We've got it here. The 144, it does this here. So 36 does the same thing. Okay? So we don't need this information. But this column here just continuously repeats. And you'll find that there's a weird zigzag pattern that occurs. Again, these 3 columns, that's all you need. That's why we're looking at these numbers now. We're just turning them into dots. It's that simple. I mentioned a second ago that we're observing a doubling sequence. Well, let's start with simplicity. Vertical lines. Can't get any simpler than that. I also mentioned the addition-subtraction that occurs. Because we're looking at three columns only, we only need these 3 points. And in this case, we'll call this the 180, this the 108, and this the 72. So 72 plus 108 equals 180. Yeah, this is just a straight line, horizontal, simple. But 108 minus 72 equals 36, which is why this triangle exists. And you can do this for all of the numbers that exist. Every row you can find that will work. So the 108 minus the 72 equals the 36. Moving on, we're going to observe some triangles and how they overlay each other. For the purpose of this exercise, we'll consider this point here, and this point here as the 9, the 54, and the 45. So this will be the 9, this will be the 54, and this will be the 45. I'll just quickly show you that here. We have the 9, the 54, and the 45, which translates to this. But you can obviously shift this down or shift it up. And in doing so, you create this overlap section that occurs. This all becomes relevant later on. Triangulation is something that is quite common. Oh, I forgot to mention, obviously you're looking at the simplicity of it. So 54 minus 45 equals 9, or 9 plus 45 equals 54, or 54 minus 9 equals 45. How do you choose to observe the information? You can use negative numbers as well if you want. It doesn't matter. In this case, we have the 9, the 45, and the 36. I'm trying to start from 9 on the first few that I do for a good reason, so that you can see that there is like a starting point. The number 9 is extremely relevant in the pattern, even though 108 and 72 are key numbers. So 45 minus 36 equals 9. See? Simple. And then you just join it together. If you were to add all three of these numbers together, the 9, the 36, and the 45, you get 90. 90 would exist right here, where this dot is, which would mean you'd have a line that goes here, a line that goes here, and a line that goes here. We're not observing that at this moment in time. We're trying to keep it simple. So in the case of this, we have the 9, the 36, and the 27. So let's have a look at all these numbers together. We have the 9 here, the 36 here, and the 45 here. So we can easily triangulate with that. But we also have the 27 that sits right next to the 45. So we can triangulate again there. We're looking at simplicity. Same as before, if you take all three of these numbers and you add them together, you're going to get 72. Conveniently, 72 is a part of the system. We know it sits above the 36, where this 9 is currently sitting. We'll forget that that 9's there. We'll just call it the 72. And then you'd end up with a line that goes there and then a line that connects to that. And that's all that it's going to be. But now, what we're going to look at is what happens when you overlay those two triangles. As you can see from this example, we'll take the 9 from here, the 45 from here, and the 36 from here, and the 27 there. Okay? So the 9, the 45, and the 36, and the 27. And you can see how that triangle, and then it shifts down, and it shifts up. You don't just have to create triangles. You don't just have to work with numbers that fall back into the system itself. We're going to have a quick look at a rectangle. 360 plus 216 plus 864 equals 1,440. 360, 216, 864, 1440. And there's your triangle, rectangle. With the rectangle, you can obviously draw lines that go through the center of it, as I've shown you here. There's other ways to find that information, though, as I'm about to explain. This is a burst pattern. In the case of this, we have one column that is not being used. We'll call this the 108 and this the 72. We're using multiplication, and we're now looking at numbers that exist outside of the system itself. For good reason, too, because otherwise it would get boring and complacent if you were stuck in the same loop. 108 multiplied by 72 equals 7,776. I will be discussing this number later on in another video. To take this pattern and shift it down by 1 point, you achieve the result of 1944, which would be 54 multiplied by 36. To take this pattern and shift it up by 1 point, you would achieve the result of 31,104, which is 216 minus 144. What's really happening is you're looking at something that is doing this. And then obviously it's doing the same thing that way. Because 54 times 144 is 7,776. 27 times 288 is 7,776. Same thing happens the other way. And then again, whether you move it up or down, it doesn't matter. We're going to have another quick look at a different burst pattern. In the case of this one, we're using the 180 and the 72. 180 multiplied by 72 equals 12,960. If you know anything about the number 12,960, I will be discussing that in a later video. To take this pattern and shift it down by 1 point, 90 times 36 equals 3,240. And that will be a result as long as you follow the same idea. To shift it up by 1 point, which would be the 360 times 144, gives you 51,840. And again, the same thing's happening. It is possible to find a burst pattern that exists the other way around. I didn't feel it relevant to have to point that one out because I'm going to show it to you here. This is the three major burst patterns that you're going to find of the similar nature. You'll notice that the major one that uses the 180 and the 72, it bursts from the 108. When you do the burst pattern between the 180 and the 108, it bursts from a point that exists between them, which would obviously be where this line is. I think it's fair to say there's information that exists between these two numbers. And same again with this, which is why the burst pattern, in the case of the 108 and the 72, bursts from a point that exists between the two numbers. Now, personally, I know that with this information right here, I have everything I need to find the platonic solids. I know that sounds a little bit crazy. How can you find the platonic solids with something like that? It's there. Now, I'm so kind, I'm so nice, I'm going to show you a mess. It's a beautiful mess. I'll explain what it is in just a moment. The main reason why I want to show you this right now is to give you an idea that you can easily find something that appears to be an octagon, but it's missing one line. The burst patterns I just showed you will clarify that one line. It's about taking all of the information and laying it down together. And regardless of which version that you're looking at, obviously I'm using the 108 and the 72 as the key, you can take the number 90 and you can put it in the center if you want. You can take this entire column, shift it into the center and up by 1 point, and every single number here will fall perfectly in line horizontally. So in the case of this right here, what is it we're actually looking at? It's simpler than you might think. Here we have one triangle, one simple triangle. For the purpose of the exercise, we'll use the number 9, 5.625, and 3.375. One triangle. But what's all the rest of this stuff then? Well, it just so happens to be this thing here. The The linears that go through the internal of the object will get discussed in the next video called the Platonic movement. Six-sided object made of triangles. Triangle number 1, triangle number 2, triangle number 3, triangle number 4, triangle number 5, triangle number 6. This one here, as you're observing it, this triangle right here happens to be the one that it's sitting on. That's the base that it's sitting on right now. This triangle is actually lifting up into the air and pointing at you. How clever is that? Obviously, there is also this triangle, which appears, but it's not actually there. It just appears to be there. Clever. A moment ago, I mentioned creating an octagon. In the case of this right here, we're simplifying. We've already looked at the burst patterns. We're not just looking at a halving doubling sequence. We're looking at something that expresses quarters. So, for the purpose of the exercise, how about we take one triangle and turn it until it comes back onto itself? Seemingly a little bit of a cheater's method, but it does definitely create an octagon there. As I mentioned before, you do not need to do this here. The information that I provided with the hexahedron and the triangle that overlays it and the burst patterns alone, that will give you all of the information that you need to find the octagon and much, much more. Hang on a second though, because I mentioned at the beginning that we're going to look at something which is going to express two-dimensional, three-dimensional, and beyond. We're working with something that is pentagonal form. Okay, so there's two-dimensional obvious, yeah? Triangles keep appearing. I showed you a rectangle. That's definitely two-dimensional. I showed you a six-sided object which is three-dimensional, made of triangles. Perhaps then, what we should do is consider this. I mentioned a moment ago that if you wanted to, you can take the number 90 and you can put it in the exact center of the 180 and the 72. In fact, you can take that entire column, shift it over into the center of those two columns with the 180 and the 72, and up by 1 point, and everything will be numerically descending in a horizontal fashion. We're looking at something that is expressing, at the very least, a square and a circle. Circles and straight lines, that's everything. Everything I look at is circles and straight lines. And in the case of this, well, we know for a fact that if you look at a square, you can also observe this one here. I'll talk about that in another video. We know that we can create 4 units of 90 degrees from this one point. We also know that 2 units of 45 exist when you do the line that goes straight through like so. But in reality, this angle here is a 90-degree angle. Externally, it's a 90-degree angle. The circle itself is 360 degrees, and these 4 units of 90 degrees, or these 4 units of 90 degrees, depending on how you want to observe it, is showing you 360 degrees. So I think it's fair to say we're looking at something that is definitely exposing two-dimensional. But I also said that we're looking at three-dimensional and beyond. And then I showed you how three-dimensional appears. Well, then we need to observe these 3 lines. It's interesting to note that the actual angle here is 60 degrees. And yet I've got 90 written right here. So why is that? Well, this line here, when it interacts with these 4 lines, creates 4 units of 90 degrees, because we're looking at the dimensional properties, 3-dimensional space, isn't it? When these four lines interact with each other on that one flat plane, you create 4 units of 90 degrees. This is merely an overhead view of this right here. When this line here interacts with these 4 lines, you create 4 units of 90 degrees. Thus, we have 12 units of 90 degrees. 12 times 90 is 1080. Does that help to explain the octagon that we were looking at a moment ago? Because that is an octagon, isn't it? 1080. 135 times 8 is 1080. Interesting. For the moment, we're going to move on. Lots more stuff will be explained hopefully later on in this video and in later videos that are to come. I mentioned that you can change how you observe this whole pattern. So the numerically descending, in the case of the one that we're observing, it zigzags. Then we have multiples of 5 and multiples of 10. When you actually put these down, they will overlap each other. Multiples of 5. Well, 9 times 5 is 45. 9 times 10 is 90. 144 times 5 is 720. 144 times 10 is 1,440. It's actually really simple. In fact, if you wanted to start looking at multiples, we could do this. 9 times 2, 9 times 4, 9 times 8, 9 times 16, 9 times 32, 9 times 64, so on and so forth. Or you could do this. 9 times 3, 9 times 6, 9 times 12, 9 times 24, 9 times 48, 9 times 96. Interesting. I like that. What I just showed you is background information that's happening within the system itself. We have multiples that, when you look at the numbers that I just said, are literally expressing the 124875 right here. You look at the multiple, you break it down into its root number. Everything in this is based on a root digit, by the way. Yeah, root value, everything. So if you take the multiple and you break that down into its root digit, you're going to find the 3636. So you got the 124875 and the 3636, and it's all based on the 9 here. And that comes from VBM, vortex-based mathematics. Back to this. When you observe the numerically descending and the multiples of 5 and the multiples of 10, well, to me, that's all the information that I need to find the Platonic solids. That's twice I said that. Yeah, I know. It's crazy, isn't it? So let's have a look at what happens. And because I'm such a nice guy, I didn't just apply the multiples of 5, multiples of 10, and the numerically descending. I also applied the doubling and the addition-subtraction. You know, the subtraction part isn't that relevant because this line here, and then it repeats again, that is, it's already a part of what we were looking at, which is the multiple of 10. The numerically descending, is zigzagging, like this. So your multiples of 5 and your multiples of 10. Now, the doubling sequence is obvious, and your addition-subtraction is also obvious, which creates really nice squares and even better information. Because I said to you that I only need the numerically descending and the multiples of 5 and multiples of 10. 6 lines, that's all I need. 6 lines. I love putting this pattern together like this because when you turn it like that, it gives you really good information. Yeah. Here's what I made earlier. So what I've done in this one, I haven't included most of the stuff that we've looked at. All I've done is provide some information. one of the things I did try and focus on was making sure that the octagon appears inside of here, because I want the octagon to be seen, because it's there, it's a part of the system. The key thing that we need to look at, though, is this right here. It doesn't take a genius to work out that we're observing a cube from this perspective. What's all that other information? I'll tell you in the next video. Platonic movement. If I can find any one Platonic solid in two-dimensional or three-dimensional, I can show you all the rest. I can show you shapes that exist outside of the Platonic solids. What I'm going to do now, though, we're going to talk about the Pentagon. Because it's obvious, isn't it? The 108 and the 72 is pentagonal form. This is a perfect pentagon, isn't it? Right? Well, watch this. 36 plus 72 plus 144 plus 108 plus 180 equals 540. Well, that's the numerical value to a pentagon, isn't it? 108 times 5 is 540. Interesting. Let's take this pattern and shift it up by 1 point. 72 plus 144 plus 216 plus 288 plus 360. That gives us 1080, which brings us back to the octagon again. But it's not an octagon that we're observing. No, in fact, what I just did, the reason why I called those numbers out in the way that I did is because you're looking at the perfect value to find a pentagon inside of a circle. Interesting, because we seem to have found a relationship between the octagon and the pentagon within this system. Let's take these numbers, let's translate them into a pattern. Well, that's interesting, because that's not a pentagon, is it? I will explain how this grid comes into play later on. There's a reason why I'm saving it for later as well. It's because it's key information for something else. That's a tetrahedron, isn't it? Yeah, that's a tetrahedron. But there's something missing. The number 144 is blatantly a part of the numerical values that we were observing, right? In the case of the triangle using the 9, the 45, and the 36, the 9 exists here, the 36 here, and the 18 in the center. The 18 is not being used, so you don't need to worry about it. But the 144 is now being used. So, let's use it. Wow. You know what? I'm going to turn it like this. This is a perfect square using diagonal lines. That's one of the reasons why I showed you the square I did earlier when I was explaining the dimensional properties. By using the number 144, when you create your 4x4 grid, you'll find every point, which is the halfway point of the edges that you've already drawn, will fall perfectly in line with the grid. Yeah, it creates a cube. Yeah, we're looking at a tetrahedron. You can find an octahedron in there if you want. You can find a dodecahedron if you want. Okay, come on, let's face facts. You know that I'm going to tell you about this pentagon right here. See that pentagon? That's a beautiful pentagon. It's not a perfect pentagon. It's really, really beautiful though. See? Oh, did you think I was going to tell you about that one? Yeah, of course I am. Here is the interesting part. I spent a long time looking at circles and straight lines in two-dimensional, three-dimensional, and beyond. And I spent a long time observing it from this kind of perfect perspective also. In doing so, everything lines up here in the exact center, which is why you have these three pentagons that exist on the inside. They're not the only pentagons that you can find in this, but they're there. Yeah, we can observe a cube. Yeah, we can observe an octahedron. Yeah, we can say that's a dodecahedron. If you know how to use these 15 lines within this territory right here, although they haven't been completely finished, you can find an icosahedron. This here, from the mathematical formula that flowed through me, showed me something completely different. It's not going to be easy to show you using this. Let's try. So here we have the three pentagons that come into play, one of which exists in this area, one in this area, and then obviously the other one sits over there. And that's this view that you're observing, like so. Okay? That's not a very good view of it, my apologies. Try and line it up straight, it's so hard. But in this version here, it's actually being observed like this, which is why this here, this here, this here, and then these two edges become the pentagon. I've had that shape hanging in my home more than 4 years. Just that one. I've got loads of different tetrahedron for lots of different reasons. That one has been hanging in a spot where I walk past it multiple times every day. It wasn't until I started working with the formula, and then it showed me how to create the grid, and then it showed me how to find this pentagon, that I realized there was pentagonal form inside of that tetrahedron other than the ones I had already been observing. I truly hope that you like what you've seen so far, and even though not everything has been explained, I'll do my best to finalize more information about this formula at a later date in other videos. For now though, just know that the next video I will be doing is the Platonic solids. It's called the Platonic movement, is the name of the video. And it's going to be a completely different perspective, a new perspective on shapes and patterns. See you in the next video.